So let's take a look at the packing in a face-centered cubic structure. So I've got here just kind of a little demo that I wrote showing the face-centered structure. Here's for a single unit cell, for example. So you can see the cubic structure, and you can see that in the face of this cube, you've got an atom. Okay? So a face-centered cubic structure. So we're going to add on a bunch more unit cells so we can kind of build up our crystal. And one of the things I want you to notice is that depending upon which direction we look at this crystal, we're going to have a different placement of atoms. So for example, I just want to highlight the faces. So you can see the faces have this square geometry. It looks like the 5 on a die. But if I was to look, say, along one of the diagonals of this structure, so I'm going to slice it in a different direction. You can see now I've got, again, a nice plane of atoms. Okay, but now they've got a triangular, or if you want to look in here, you'll see that there's a hexagonal pattern to the structure. Okay, so each direction that we were to slice this material, let me slice it yet again one more direction. This is now cutting off an edge. You can see that edge now also forms a plane when I cut that edge off, and my atoms have, again, another symmetry that you don't see in the others, and different packing. This is a very low density packing. In fact, let me go ahead and remove the atoms so I can just look at the planes. You can see this is a pretty low density of atoms. Right? They're not even touching in this direction. It's just like rows. Then if I look at the face, this is a higher packing density than this one in blue. That's our 5 here on our die. That's our face. And then if we go ahead and look at that slice through the body, through the diagonal, cutting off the diagonal, the corner, we now have the closest packed plane with that nice hexagonal symmetry or triangular symmetry, depending on how you describe this. This looks a lot like the packing of billiard balls, right? So if you take a look here at these atoms, this would be your billiard ball rack. So this is the most efficient packing in 2 dimensions. All right, so what we're going to learn in the next video, is how to describe each of these different planes. Okay, we want some way of describing them. And we're going to use these special indices. And so when we mentioned the 1, 0, 0, this is a face. The 1, 1, 0 is cutting off this edge. And what's called a 1, 1, 1 is cutting off a corner. But we'll get to that. Okay. And this demo also allows us to take a look at the body-centered cubic. You can see that the packing on those planes are completely different than what we had on the face-centered. Everything is much more open. And now this blue one, this 1, 1, 0, now looks like the best packing in 2D. In fact, this is the highest packing in the body-centered system. Right? In the face-centered, it was the red plane, 1, 1, 1, that had the highest packing. So we'll come back to this a few times as we go through the course. All right. So let's go ahead and go back to our slideshow. This slide here is just showing what I just showed you in the Mathematica demo, so I'm going to go ahead and skip this one and talk about this question of what is an ABAB packing versus an ABC packing. So this is where we explain that. So this is a slice across the corner. Okay, you can see again that triangular or hexagonal symmetry that's in here. And so this is for the face-centered cubic system here. So let me go ahead and label that. And the one over here is going to be for the hexagonal close pack system. All right, so let's just go ahead and call this plane A. Okay, and this one over here is just A. And then we're going to go ahead and build another set. Take another set of billiard balls, put them in your rack, put them on top of the previous one, and they'll naturally fall into the hollow site in between 3 atoms below it. Okay, forming a little tetrahedron here, these 3 red ones below and this green one sitting on top. Okay, so that's my next set of planes, and I can do that over here as well, so everything is identical. And then what I've got is my next set. I actually have a choice. Okay? I can go ahead and place my next set of atoms, say, in this hollow site here, or I could place it, say, in this hollow site here. Okay, I can't use both because the atoms won't fit, but I have a choice of which ones I use. So this one here would repeat the red layer underneath. Okay, now sitting on top. This site here is unique. It doesn't repeat the red layer below it or the green layer, and so this is a third choice. So we refer to this then as layer C. Okay, that's what the face-centered cubic structure does. So this is just say an A plane, B plane, C plane. And it's arbitrary what we're calling ABC. It would just mean that there are 3 unique orientations. And then when I continue on, the next plane that would go on top of here would then be A again. And it repeats this ABC. So if you build up your planes this way, then you could rotate it around in space and you would see that it would create the face-centered cubic structure. All right, over here, the hexagonal close packed, what we're going to do is not use this third layer, C, but we're going to go ahead and repeat the first layer, the A layer. Okay, the red ones again. And so this is referred to then as this ABAB packing, and it just continues. When I do that, if I was to look in the crystal, I will no longer see this face-centered structure at all, but instead I will have this hexagonal packing. Okay. Both these structures have the same packing density, that's 74%, the atomic packing factor, 0.74, because they're made the same way. Okay, but they have very different symmetry. And so what I want to show you is that this change in symmetry, okay, but again, no change in packing density, results in a very large change in the mechanical behavior. Okay, so I'm going to show you the idea here again, that structure is going to affect, in this case, property or mechanical property. So here I've got a material that has the ABC packing. This is face-centered cubic. This is aluminum. And over here I've got zinc, which is HCP following the ABAB packing. Okay. Both of these pulled in tension. You can see that the aluminum behaves in a very ductile way. You can see a lot of change in the diameter across the sample as it failed. You can see a lot of distortion and what looks like a cup and a cone. Okay. A lot of ductile failure. When you pull on the zinc, this is just showing the bottom half now of it, you can see what you get is a brittle fracture. You get a nice flat cleavage plane across here, a little bit of ductile tearing at the very end. But this is what is indicative of a brittle fracture, no change in the cross section. So again, this is just due to the packing difference. Now, if you're thinking ahead a little bit, you might say, well, I changed the structure too. I changed the material, right? So how do I know this is due to structure, this difference between face-centered and hexagonal, when in fact I actually went and changed the material? So that's 2 variables, right? So I'm going to take a look at the case of tin on the next slide here. Tin has 2 forms, or which are referred to as allotropes, just meaning it can have 2 different structures. Okay, so now in this case, I have the same material, but 2 different structures. Okay, so we have another structure called tetragonal, which has the stretching of one of the edge lengths. This is supposed to be a square here. It looks, I know, rectangular, but it just stretches the one edge length, still 90 degrees on all the angles. This is referred to as a tetragonal structure. You can read about that in your text for the other systems. And it has an atom in the center, so it's called body-centered. It's a body-centered tetragonal. This is what's referred to as white tin. You can see a tensile sample that's been machined out of white tin down here. We also have what is called the diamond cubic structure. So this is a cubic structure. So here's a cube. And it also has atoms in the center of faces. So it's like a face-centered cubic, except then it also contains an extra set of 4 atoms, 2 on the bottom, and there'll be 2 up top. So again, it looks like face-centered with an additional 4 atoms. So this would have, for example, 8 atoms in this unit cell rather than 4. And I know this picture is pretty tough to see. We'll take a look at this in other ways later and try and be able to see this in 3D, because this is a really terrible picture, confusing. So if you have trouble seeing this in 3D, don't worry about it yet. Okay, but this is called diamond cubic structure, right? They have different densities because of the different packing. And you try to make a tensile sample out of that, and it just crumbles. Okay, so this structure is very, very brittle. This structure is ductile. So, okay, so that's just showing you again the effect of structure on, in this case, mechanical properties. So it's pretty interesting stuff. And as we go on, we're going to go ahead and explain why this is the case and why does structure affect these properties so much.